Yes, in this video we want to focus a bit on the basic terms and notations that we need to engage in probability theory. And we will start right away with a very important concept, that of the random experiment. And you will see that now this is not a precise definition, but rather, I would say, more of a prose explanation of how I will explain it. But it is simply because defining everything in a truly abstract way goes far beyond the scope of the course. I think we should be able to handle that well. So, a random experiment is a process that has various properties. First, we can repeat it any number of times under the same conditions. I can perform this experiment as many times as I want, so to speak. It doesn't just disappear at some point. Rather, I am able to carry it out any number of times. And it is supposed to include the word randomness. This does not mean that there is no determinism, but rather that we cannot predict the outcome of the random experiment with certainty. So we cannot say with certainty what the outcome will be, which is why we need probability theory to at least make statements about frequencies. And exactly. The standard random experiment that I will frequently conduct in this lecture consists of two different ones, both of which are very classic. This is the coin toss. I can toss a coin multiple times, and I cannot say with certainty whether it will land on heads or tails. And the other very popular random experiment is the dice roll, which is essentially the same. I can also repeat the dice roll any number of times and cannot say with certainty what the outcome will be. The only difference is that there are 6 possible outcomes in the dice roll, while in the coin toss there are only 2, which makes the coin toss a bit easier. Okay, so that is a random experiment 2001. Next, we want to discuss what outcomes can arise from such a random experiment. And the set, so we are talking a lot about set theory here, the set of all possible outcomes of the random experiment is called the sample space, or also event, or simply set, or outcome space, and we typically denote it by omega. Let's do an example to clarify this. In the coin toss, there are 2 outcomes, while in the dice roll, there are 6 outcomes. That is omega. And now there are outcomes, and a very, very important concept that is not intuitively clear is the concept of an event. And I will write it down like this. An event, which we will often denote with A or with a capital letter, is nothing more than a subset of our sample space 2001. So indeed, all possible subsets of omega are events. Okay? That means, for example, in the case of a dice roll, an event can be 1 in the second, because 1, 2 is a subset of 1, 2, 3, 4, 5, 6. However, let's do another example, a bit more explicitly. We can now talk about whether an event has occurred in detail. And we say that an event has occurred when the outcome of a random experiment is an element of A. An outcome is, so to speak, 1, 2, 3, 4, 5, or 6 in the dice roll. Let's say we take the event that consists of 1 and 2, then this event occurs if either 1 or 2 is rolled. At the same time, we have the sample space, and now there are special events, namely those events that contain only one element. So they contain only one element. And these have a special name. They are simply called outcomes, or one can also refer to them as elementary events. That means events can consist of multiple elements, while outcomes are always single element subsets. We also call them elementary events. Exactly. Now there are special events, which are the subsets of omega. The set omega itself is also an event, because omega is a subset of omega, and this is the event that occurs in every case. And it is therefore also called the certain event. Logically, so omega is the certain event, because it occurs in any case. And now you can already guess that the next thing we will look at is the impossible event, which is the empty set. The empty set is also a subset of omega, and it is the event that never occurs. And we call this the impossible event. Alright, and now let's do an example. So we are now taking the random experiment of rolling a die. We take the dice roll, and first we look at the sample space. I'll write this down in black. This means we have our omega, and there are 6 of them, which I will label as 1, 2, 3, 4, 5, 6. Yes, depending on which number is rolled. Okay, let's take a look at what the elementary events are. If you remember, those were the single element events. So that's 1, 2, oops, I wrote it down incorrectly, 2001. The 3, the 4, the 5, and the 6. Yes, so these are, so to speak, events with only one element. Yes, and then there are of course more events. Can you think about how many events there actually are? I will give an example. For instance, we can take the event that the number is even, which means it is 2, 4, or 6. Or we take the event that the number is odd, which would be 1, 3, and 5. Yes, and you can consider how many events there actually are. But exactly, essentially they must form a subset of omega. Well, these are the terms events, outcomes. And when something occurs, and what I can do now is, since events are sets, I can combine them. For example, I can say that I want to consider event A and event B, or event A or event B. And we should consider what this means as a mathematical concept, as a set operation. And there we have first the event A and B. And well, the event A and B should occur if both A occurs and B occurs. And that is of course the case when it lies in the intersection of both. Okay. So A and B correspond to the intersection of 2 events. And now you can think about what OR means, and that is of course the union. Either A occurs or B occurs. This means that the new set is A union B. Now there is indeed also the complement which occurs when A does not occur. And we now denote this with a bar. Be careful not to confuse this with the arithmetic mean, which is a completely different term. However, we usually do not mix them up, as the arithmetic mean is typically denoted by x. And here we have capital letters. Yes, so this is the complement. This is, so to speak. I don't even know if I write it there. Yes, exactly. This is then omega. Without A, this is the complement of A. And now we have 2 different terms, namely compatible and incompatible. When is something incompatible? When it cannot occur simultaneously. And that means nothing other than that the intersection of the 2 sets is empty. Then events A and B cannot occur simultaneously. We call the sets incompatible. Otherwise, we call them compatible. Then there is, so to speak, a possibility that A and B can occur simultaneously. Well, yes indeed. Then let's take a look at a short and simple example. We consider omega, which can be sunny, rainy, cloudy, or snowy, so it is about the weather. And we have here events A, B, C, and D that are present. A occurs if it is raining or sunny, B occurs if it is sunny, C if it is snowing, and D if it is cloudy. And now we can ask, what is A intersection B? So, what is A and B? And that is, of course, if it is sonic. What does A intersection C include? Well, that means A or C, so rain, sunny, or snow. This means that we have rain, sunny weather, and snow, for example. What weather occurs with D bar or D bar? Yes, exactly. D is cloudy, which means that the opposite of cloudy is sun, rain, and snow. And are B and C compatible? This means that B and C have a common outcome, so they can occur simultaneously, which indicates that they have an intersection that is not empty. Event B is sunny, event C is snow. The intersection is the empty set. Thus, they are incompatible. Okay. Yes. These are the most important terms that you should internalize before we move on to the axioms of probability and the concept of probability in the next step. Until then, take care.